Welcome to Chemistry 111. Today we'll go through some of the homework for the last chapter, the gas phase chapter, and we'll start looking at the old test. To say, like, test will probably be next week. I'm shooting for Thursday. The test is already written, however. So if you know you won't be able to make it another Thursday evening exam, come take it early. Come take it a little bit late. I don't care. I don't care how you have to make it work. Make it work. I don't want to have to come hunt you down. So please plan accordingly. That's what I'm going to shoot for again. Another Thursday exam. For those who are in lab, don't forget to be turning in your online labs. Thinking about that. I don't want to be slammed with like 30 of them come into the semester. You can work with your partner if you want to. Accepted like a group online lab. If it helps you get them done, get them done. Go ahead and get started. Okay, here we go. A quick reminder that I have already posted the crib to last year's exam, to the exam 3. So that's up there on YouTube. We'll be working on that. Okay. Now this chapter 11 homework is split into 2 parts. Part A and Part B, both worth 50 points, but various difficulties. Part A is only 7 questions. I'm not going to do all of these. Some of them are pretty self-explanatory. Like, perform the conversions. You need to turn millimeters of mercury into atmospheres. There's a hint. All the conversion factors can be found on this table. I'm not going to do this one because of how easy this actually is, but note that I'll do maybe one of them. Maybe one, maybe 2. I'll do the millimeters of mercury to atmospheres and kilopascals to atmospheres. And please note your numbers will undoubtedly be different. Millimeters of mercury to ATM and 785.8 kilopascals to ATM. Okay. Going to the .cam. So one conversion is there is 760 millimeters of mercury in 1 ATM. That's all. There's also 760 torr in 1 ATM. So to convert this into ATM, I'm going to say 760 millimeters of mercury and 1 ATM. So 978.1 divided by 760 is going to be 1.287. Now, kilopascals is a little bit harder. Kilopascal is the same as, so that's actually saying 785,800 pascals. Now there's 101,325 pascals in 1 ATM. So to do this one, we got to take this number divided by 101,325 pascals. Or otherwise, 101.325 kilopascals per ATM. I'm not sure what the table's going to give you. So I'm just saying 785,800 divided by 101,325. So that's going to be, well, that's 7.755 ATM. I'm using four significant figures because our original starting number had 4 significant figures. However, I'm not sure the problem itself will be that picky. So as I said, you can do these conversions, atmospheres to torr, millimeters mercury to Pascal. So you might, for the millimeters mercury to Pascal, you might have to turn it back into atmospheres and then turn it into pascals. But it can be done. So some of these problems will just be like individual laws put together. Like the volume of a sample of hydrogen gas was decreased from 14.6 liters to 7.9 liters at a constant temperature. So this one is Boyles Law. If the final pressure exerted by the hydrogen is 7.7, what pressure did the hydrogen exert before the volume was depressed? So the hint hence you that's P1 at V1 equals P2 V2. So you got to be able to read and say, okay, this is a volume. This is the initial volume. This is a volume at step 1. This is the volume at step 2. Then it says the final pressure. So that's the pressure at 2, 7.7. What's the pressure at 1? Once again, I'm not going to solve this one, but I'll pull up the dock camera just to show you how I've set this up. How to set this up. So we have P1, I'm writing the numbers down, 14.6 equals 7.70 times 7.9. Pulling up the dock camera. We see right here, saying that pressure at situation 1 times volume at situation 1 is equal to pressure at situation 2, volume situation 2. Well, we're looking for the pressure, the initial pressure, when the volume was 14.6 liters. So if the pressure at situation 2 is 7.7 atmospheres, and the volume at situation 2 is 7.9, we can figure this out. So all you'd have to do mathematically is you'd say 7.7 times 7.9 divided by 14.6, and that would be your answer. Your numbers, once again, will probably differ. However, this is not something that is meant to truthfully challenge you too much. You need to learn how to set these up, but it's not meant to be overly tricky. Now, this one, we have a volume and we have a temperature, and we have a volume. So this one is similar, except the equation is V1 over T1 equals V2 over T2. So I'll go ahead and just write that out. I'm not even going to solve this because I want to save time to do other stuff. But once again, with the dock camera, you'd have V1 over T1 equals V2 over T2. Basically, it's coming from the PV equals nRT, and we're separating the variables from the constants. So we're saying if we get V and T on the same side of the equation, we're setting it equal to N, R, and P. Well, if that is held constant, we can set that to another V and T situation. In this case, we are not given T2. We're not given T2, so how are we going to solve that? We have to get T2 to the other side. So the equation will look something like T2 equals V2 over V1 times our T1. Something like that in the end. Please note the temperature must be in Kelvin, but for this problem, temperature is already kept in Kelvin. so you don't have to worry about that. Do an actual problem, either this next one or, let's see, I'll go ahead and do the next one. An ideal gas is sealed in this 2.7. This is 18 degrees C. The final volume is 1. Okay, let's read this again because I just glossed over some of this. An ideal gas is sealed in a container with an initial volume of 2.7. So V1 is 2.70. At a constant pressure, it is cooled to 18 degrees C. Whereas the final volume is 1.75. What is its initial temperature? So we aren't given T1, we are given T2. This one is a little bit harder, and only that it gives you Celsius and expects you to answer in Celsius. What you want to do, what you naturally want to try to do, is probably like leave it in Celsius, but everything has to be converted into Kelvin. So V1 over T1 equals V2 over T2. The first step we got to do is we add 273 to our Celsius to get 291 Kelvin. So plugging this in, we have 2.70 over T1 equals 1.75 over 291. So with that in mind, T1 is equal to 2.7 times 291 over 1.75. 0.7 times 291, 1.75 gives us 448. Let's say 448, 449. We'll round to 449. Now, because they ask for the temperature in Celsius, we have to then T1 minus 273 to get it back into Celsius. So we're going to say the final temperature is 176 Celsius. So we had a hot gas, we chilled it quite a bit, and it went down to a cold gas. Well, at least a room temperature gas. I know it's really hard because it's like, oh, like it seems like oh, what the heck? Okay, let's see. 18, let's see. Let's see. That's 273. Okay, let's see. 2.7 divided by 291. 2.7. 91.15 divided by 1.7. Okay. See, just looking at what went wrong. 1.5. Oh, geez. That's what. Good Lord. Easiest mistake in the world. I somehow put a decimal in there. Instead of 176, I did 1.76. Okay. So, yeah. Now, this one is just recognizing from the PV equals nRT what values are directly proportional versus inversely proportional. So to be directly proportional, they have to be on opposite sides of the equation. To be inversely proportional, they need to be on the same side of the equation from each other. So looking at PV equals nRT, I'll just give you two of them. P over T, P and T are on opposite sides of the equation because you have PV equals nRT. So that'd be a direct proportional. Now, P and V are the only ones given here that are on the same side of the equation. If I said N and T, then you could say, though, those are inversely proportional. But the rest of them you can figure out. Okay, and then from there, the last two problems are ideal gas equations. So if 73.5 moles of an ideal gas is at 2.79 atmospheres at 339 Kelvin, what is its volume? All you have to do is just get used to using the PV equals nRT and arranging that. So you see it V equals nRT over P. R, in this case, 0.08206 ATML over mole K. Okay. So plugging that in, 73.5 times 0.08206 times 339 divided by 2.79. These problems often have to do with first recognizing what equation you have to use. Two, second, you have to then identify the variables we're given. And then three, arranging the equation to solve for our unknown. And then four, just plugging in and solving. So I recognize I'm given moles, pressure, temperature, and asked for volume. I know it's an ideal gas equation. I've isolated the volume, and I've identified my three variables and one constant. So in this case, my answer would be 732.8 liters. A huge volume, mind you, but it is a large amount of gas held at a pretty high temperature. 732 liters, you got to remember, maybe that's the size of the room I'm in right now. I don't really know. I'd have to look at the cubic feet of space. How high is the ceiling? How much floor space do we have? But okay. Once again, moles, liters, temperature, what is pressure? The only problem here is they give us temperature in Celsius. So I'm going to skip this one and we'll move on to the part B. As I said, part A is relatively straightforward as far as some of the homework goes. Part B is when we get into some of the more unusual equations. I mean, that's the nature of a lot of these problems, though. A lot of these problems in this chapter is you need to recognize we're going to have a bunch of different type of equations. You need to first be able to read the problem carefully, determine what equation we need based on the values given. Then we have to define what value goes with what situation. That's something we'll see as we work on the test, something we'll see as we work on this homework. We have specific equations depending on what's given. Okay, here we go. This one, also 7 questions. Not too bad. It starts with Dalton. Dalton's pressure. The mixture of helium, neon, argon has a pressure of 25.9 atmospheres at 28 degrees C. So P total is 25.9. The pressure of helium, so pressure helium is 1.13. The pressure of argon is 2.18. What is the pressure of neon? In this case, they've given us one bit of information too much. We do not actually need the temperature. We are just going to use the fact that P1 plus P2 plus P3 equals P total. So we have 25.9 equals 1.13 plus 2.18 plus whatever the pressure of neon is. So 25.9 just becomes minus 1.13, 2.18. So a lot of this ends up being neon, 22.59. So don't overthink some of these. Some of them, they will give you extra bits of information. But the whole idea of Daltons is we can, if you have total pressure, you have a sum of a pressure, figure it out. Okay, this one's also, I think the next couple are Daltons. This one is maybe a little bit harder. 3.09 grams of argon, 3.09 grams of argon are mixed, and 3.56 grams of krypton are placed in an evacuated 2.50 liter container at 25 degrees. 25 degrees. What is the partial pressure of each gas? What is the total pressure of each gas? So it may not look like we have all we need, but we do. We do actually have all we need. We just need one more bit of information. What's not obviously clear, but it's there. This is a PV equals nRT. So we're given the V, we're given the T, we're not technically given the N, and we're trying to solve for our pressure. But instead of given the N, we're given the mass. Well, we got to remember, moles are equal to the mass divided by the molar mass. So 25 degrees, when we add 273 equals 298. We're given the volume. That volume will not change. So all we need is the moles of each gas. So we got to look up on the periodic table. This is the one thing that's not directly given. The molar mass of argon, the molar mass of krypton. Argon is 39.9. So moles of argon is going to be equal to 3.09 divided by 39.9. And that will give us our moles of argon as 0.0774. And the moles of krypton is 3.56. The molar mass of krypton is 83.8. 3.56 divided by 83.8. That's going to be 0.0425. Now, to get the individual pressures, we're just going to say our moles times R times T over P over V. Oh, crap. What did they want? They want in atmospheres. Okay. So for the moles of argon, 774 times 8206 times 298 over 2.5. 0.0774. That the pressure is 0.757 atmospheres. Doing that again, 0.0425 times R times 298 over 2.5. And we would have the pressure from the second gas is 0.416. And then the total sum is then the total pressure, P total, is just going to be 0.757 plus 0.416. Or 1.173. So this one looks hard only because it's made up of a couple parts. By itself, part one is not meant to be too bad. Part two is just another reiteration of part one. Part three, where you add them together, once you understand part one and part two, you just have to, if you can add them together, you're good. So three is just like the one we worked on the slides. Sample of oxygen, or depending, you could end up getting a sample of nitrogen gas, was collected via water displacement, saturated water vapor. You're given the temperature, you're given the total pressure, and you're asked for what is the partial pressure of water. This one's actually the partial pressure of oxygen. This one's actually really easy. So if you're given the P total and you're told that the vapor pressure of water is 25.81, you just need to convert millimeters of mercury to torr, which is a 1-to-1 ratio, and subtract it from your total pressure. So 749 minus 25.81 is your answer. So don't look that one. That one's actually a lot easier. Though the one on the slide, we actually had to calculate some things. This one we just subtract.
What if it was to ATM instead of torr?
Oh, if we were to convert to ATM instead of torr, real quick. So, for example, let me go back real quick. Back. I need it. Okay, if I was going back to it. It would still be similar steps, like hypothetically. And if I said the total pressure P total was 1.3 ATM, and the 25.81 would still hold true, millimeters of mercury. So what you would have to do in that case is you would have to convert the 25.81 into atmospheres, or convert the atmospheres into millimeters of mercury. Either way, the conversion is going to be 760 millimeters of mercury per 1 ATM. So whichever one you converted, depending on the units of the answer. So I'm going to convert this into atmospheres. So I'd say, okay, that's 760 millimeters of mercury in 1 ATM. So this is going to be a small number. 25.81 divided by 760 is going to be 0.034. So how this is going to change that number, you're going to say 1.3 minus 0.034. So in this case, it'd be like 1.266 ATM. That's how much it went down. Not much.
Okay.
So you just have to convert them into the same units before you subtract. That's the important thing, is you must always have, when you're adding or subtracting, you must always have the same units. So you can't ever add a milligram to a gram. You must convert all of them into grams or all of them into milligrams before you add them together. So you don't accidentally say, well, I have 2 grams of this and 25 milligrams of that. Your answer isn't 27, it's 2,025 milligrams. You'd have to convert one into the other before you add them together. So. Okay. Now, the next set of problems are related to the density and molar mass. There's a hint here in that this equation says density equals pressure times molar mass over RT. Now, how do you know you need this one? You'll either see somewhere where it asks for the molar mass in the equation, or it asks for density. In these problems, this is the only time in our ideal gas chapter that we will ask for density. So gaseous compound with a density of 1.80 grams per liter at 23.9 Celsius and 1.11 atmosphere. What is the molar mass? Once again, everything needs to be in Kelvin. So we're going to add 273 onto my number to get 296.9 Kelvin. 297 maybe. Okay, once again, we have to rearrange to solve this. D, R, T, P, get those to the other side. So density times R times T over P is going to give us our molar mass. I define this as 1.8. R in this case is 0.8206. T is 290, we'll say 297, because technically it's 273.15. And P is 1.11. Now you may say, well, what happens if I accidentally use the other R? If you use 0.08314, oftentimes or not, it is a rounding error. It is not going to matter. Not going to matter. So your answer here is 39.5. 39.5. Please note, if it's asking for a molar mass, is that molar mass reasonable? Grams per mole. If you get a molar mass that's 1,000,000, that'd be a freaking heavy element right there. If you get a molar mass that's less than 1, my God, that is microscopic. I mean, the molar mass of hydrogen gas is 2 grams per mole. If you get a number that's less than 1, it means it's lighter than hydrogen. So that is something crazy. So, okay, they give you a mass, a temperature, a pressure, and a volume. Step 1, what is the volume? What is the density? Density is mass over volume. You can calculate that in an instant. Take your mass, divide by your volume. And then we just reiterate that. Now you have the density, you can find the molar mass. I'm going to go ahead and skip this because we're already running out of time. I want to at least take a quick peek at the test. 3 samples of ideal gas, all the same temperature, occupy identical containers with the same volume. Assume the mass of the particles is proportional to the size. What gas has the greatest pressure? All at the same temperature, same volume. So you have medium-sized gas, light-sized gas, heavy-sized gas. So they're all ideal. So the idea here is that if they're all the same temperature, the idea here is that pressure has to do with the number of collisions, and collision has to do with the speed. So the lighter the gas would create a greater pressure because it's greater number of collisions. I'm going to go with the lightest, the middle one. They all occupy the same volume, and we're going to assume they're collected. So, because if they all have the same kinetic energy, that means the heavy ones have to be moving slower. Okay, and this last one, it's a fusion one. If sample A, bromine takes 24 minutes to fuse through. This one's actually a little trickier than I remember. If sample A, bromine takes 24 minutes to fuse through a membrane. How long would it take the same number of moles of argon to fuse through the same membrane? So they give us a rate of 24 minutes, and then they want us to know how does argon compare to bromine? So the rate of argon versus the rate of bromine equals this equation. When we're looking at rate of a fusion, the two rates is equal to the rate of the molar mass 2, so the molar mass of my bromine, or the molar mass of argon. So this one is one step harder than normal a little bit because it gives you a time. So molar mass bromine versus molar mass argon. We looked up argon previously. The molar mass of argon, it was 39.9. Only question here is, what is the molar mass of bromine? Bromine is a diatomic with a molar mass of 79.9. So a diatomic 79.9 is actually 159.8. So the square root of 159.8 divided by 39.9 is 2. And so if the rate of what is the rate of argon if the rate of bromine is 24 minutes? Argon diffuses 2 times faster. Argon diffuses 2 times faster. So if that's the case, then it will take argon 12 minutes to diffuse through that. Should take 12 minutes to diffuse. So we got to think through what we're actually trying to say. The rate of diffusion, because argon is a lighter gas, will go twice as fast. So if it took 24 minutes before, it will take 12 minutes for argon. It's not going to take 48. It's going to take 12. So, but that was all they achieved. Obviously, we don't have enough time to look at the test very seriously. So we'll look at that definitely on Friday and Monday if we don't get finished by then. But I just want to take a quick peek. This was the test I gave last year. So I just posted this on Google Classroom. You can see it now, but let's pull it up. The idea, so we have various multiple choice ones. We have grams to moles to grams. We have various ones. What is the percent yield? How many grams of lactic acid could be formed? Some of them are a little tricky, but they're actually rather easy if you know how to do it. I might do 1 or 2 of these problems. We'll see. We got a few minutes. Anhydrous, limiting reactant, 15 grams of water, 15 grams of magnesium sulfate. How much of this Epsom salt can we form? Lab, M1V1. This is based on the lab we just did. For those who were here yesterday, this is the lab we just did. We diluted 10 mils of vinegar to 50. We titrated 12.5 mils of dilute vinegar with this molarity of base. If it took 22 mils of base, what is the concentration of the original solution? Grams of barium hydroxide do we need to make this solution? So grams to molarity. We have We have M1 V1 equals M2 V2. We have a stomach. So this is all grams to grams. Here's a Hess's law problem. Here's a specific heat problem. Delta H of reaction problem. Delta H of reaction problem. Here's the internal energy problem. Heat capacity problem. Question about what it means to be a state function. Here's the density of gas problem. Let's see. PV equals PV. Well, no, there's a fusion problem. This is the density gives you molar mass problem. Really easy Dalton's law problem. PV equals PV problem. Question just about ideal gases. Question about laws. And then this is a volume, a pressure temperature problem. And then I have a bunch of problems here. PV equals nRT. PV equals nRT, if I remember right. That's all the problems. So this one will take a little bit of time to go through. I'll go through at least the first one or two right now. Okay. Reading the first problem. The following reaction between sodium metabisulfate, big word, doesn't mean it's hard, and dissolved gold chloride. What mass of solid gold could be precipitated using 150 grams of sodium metabisulfite in an excess of gold chloride? So gold, AU, and so whatever the metabisulfite, you know that you recognize the word hopefully sulfur, and the word sodium. The sodium metabisulfite, the big thing that is not water and not gold chloride, is your sodium metabisulfate. So we have 150 grams of Na2S2O5. And we need to turn that into moles, then into moles of gold, and into grams of gold. So there's 3 moles of Na2O5 per 2. Okay. So I'm going to go to the document cam. You're going to have to look up some stuff. This is like, oh, I have to go and figure out some of my molar masses. Thankfully, I know most of these. Sodium is 23. 23 times 2. Sulfur is 32. 32 times 2. Oxygen is 16. 16 times 5. The molar mass of sodium metabisulfite is 190 grams per 1 mole of Na2S2O5. What I have to look up, and I think it's 197 or 198, but what is the molar mass of gold? Gold is 197. So what I've set up here is my starting 150 grams goes on top. I use the molar mass to cancel out that to give me moles. Then I use my mole ratio, which was 3 moles of this, formed 2 moles of product. I use this from the balanced chemical reaction. All the chemical reactions I'm going to give you are going to be balanced. You don't have to worry about that. Then from here, I'm turning 2 moles of gold into grams of gold using the molar mass of gold. So if you want a cheat sheet, write down grams A divided by molar mass A times molar mass B. And then you have to do the moles A over moles B ratio. I mean,
Ratio.
however you want to do it. You're going grams A to moles A, moles A to moles of B, moles of B to grams of B. That is the steps we are doing, and the steps we're going to do in just about every problem, as long as we're going from grams to grams. So 150 divided by 190 times 2 divided by 3 times 197. You do that, your answer is 103.6 or close to 104. And so the correct answer for the first one was D. That's all the time we have right now. We will pick this up right on Friday with number 2. We don't need the HCl. We don't need anything else. We're just turning it from sodium bisulfate, which is this compound, to gold, solid gold, which is that compound. That's all we need. Now, I want to thank you for your time. I will see you guys on Friday.